So here's some multiple choice questions to try and test your understanding. For all of these, you should think about defining the energy at the start and looking at the energy at the end and seeing how much of that energy of the system is lost to friction. So here we have a block sliding down a frictionless ramp of height h. It then experiences friction in the horizontal portion, coming to rest after traveling a distance capital D. So you can see that the sort of shiny metallic part is supposed to be frictionless, and then when we see the sort of sandy or rocky picture, that's where the friction is being experienced. Okay, so if we started from a smaller hill, think about what that would do to the initial energy of the block. Is it going to have more energy or less energy? Okay, so then whatever energy you start with, all that energy is going to be lost to friction, right? Because at the beginning you have some potential energy, maybe have some kinetic energy, but at the end, the gravitational potential energy has gone to zero when you're at a height of zero, and the kinetic energy is going to zero when it comes to rest. Okay, so if we made the height of the hill smaller, what would happen to the distance the block travels? Will it be the same distance d? Will it be less than d? Will it be greater than d? Or is there more information needed? Right, and you can answer in the pop-up that's coming up on the Vizia video. Okay, so the answer is going to be less than d, right? And we can see the reason for that. If we start from a lower height, then we have less energy to start with. So therefore, as we go from the starting energy to the ending energy, that's a smaller change. And so there's less work done that needs to be done by friction to bring the block to rest. Now, the force of friction is going to be the same no matter what. So the only way that we can make the work done by friction less is to have it go a smaller distance. All right, let's try another example. So how about here? If we have the same situation, but rather than changing the height, we make the mass of the block bigger. What will happen to the distance the block travels before stopping? Will it be equal to d, less than d, greater than d, or is more information needed? All right, this one's a little tricky. It's going to be the same distance, because if we think about, okay, the energy that we start with is going to be greater because of the greater mass, so we need more work done by friction. But we automatically get a bigger force of friction when we have a bigger mass, right? As the mass increases, then the normal force is going to have to increase, and therefore we get a greater force of friction. So because both of those depend on mass, the starting energy and the force of friction, and therefore the work done by friction, it's going to travel the same distance. Let's look at this example a little bit more in depth mathematically. So the first thing that we want to do in any energy problem is define our 2 points. So our first point, point 1, is going to be at when the block is moving at the top of the ramp. So we're going to define our potential energy to be 0, or we can alternatively say our height is equal to 0 when the block is at its lowest point. So if we look at point 1, we're going to have some gravitational potential energy, and we also have some kinetic energy since the block is already moving. So we can use our definitions for both of those. We can write the potential energy as mgh, and the kinetic energy is 1/2 mv squared. So we can see that the total energy there. Then at the end, when the block has reached the bottom and has moved through the part with friction and it has come to rest, as the problem said, then we can say, well, our potential energy is equal to 0 because our height is equal to 0, and our kinetic energy is equal to 0 because our block has come to rest, our velocity is equal to 0. So energy at point 2 is equal to 0. We don't have to worry about calculating at any intermediate points because we're not asked anything about that. We're just trying to look for the beginning and the end. Okay, so how can we relate those two? Well, we don't have energy conservation here, right? We're going to have external work due to friction. So what we have to do is write down that the external work is equal to the change in energy of the system. That change in energy is E2 minus E1, right? So we can write that down, and bring those energies that we've already defined into those two places. So E2 is equal to 0, so we put that in front. And E1 is mgh plus 1 half mv squared, so we put that there in parentheses. And we know that the external work is going to be the work done by friction, so I've labeled it W sub F now. Okay, so then we need to know what the work done by friction is, and as we said, the work done by friction is equal to negative force of friction times the displacement, which here is called capital D, so I'll use that letter to match the picture. And we know the force of friction is mu sub k times the normal force, so we make that substitution there. Now, in this case, because the normal force is completely balanced out by the force of gravity, we can say that the normal force is equal to the force of gravity, or mg. So we make that substitution. So we've got the work done by friction is equal to negative mu sub k times m times g times the displacement. So now we can set that expression equal to the one above. So the work done by friction there goes on the left, and then the change in energy expression goes on the right side. Then since we're trying to look at how the displacement changes, we can solve this for the displacement. Now we see every term has mass involved, so when we divide, that mass is going to cancel out. Both sides are negative, so we can cancel that out, and then we do our division there. So now, looking at this, we can answer both of our questions, which we answered conceptually. First, we can say, looking at the second question about how does the mass affect it? Well, mass doesn't show up in the calculation, so that means that it's going to travel the same distance for any given mass. And then we can also see that the height is in the top, so if the starting height were made smaller, which is what the question asked, then the displacement would become smaller as a result. Okay, here we have a slightly different situation where there's a dip in the frictionless part of the track before it comes back up to some intermediate height. And then there's some friction in the horizontal portion. Again, you can see in the color coding. So if we look at from point A to point B, what is happening to the kinetic energy of the block? So if it starts from rest and then it's given a little nudge and slides down, what's going to happen to the kinetic energy of the block? Is it increasing, decreasing, constant, or is more information needed? Okay, so hopefully you saw that so we can say that the gravitational potential energy is going to decrease. So in this portion, we don't have any friction, so the total energy stays the same. So as the gravitational potential energy decreases, the kinetic energy will increase. The block will speed up. Okay, now how about from point B to point C? In this case, the gravitational potential energy is increasing, so therefore the kinetic energy will have to decrease. All right, and then how about from point C to point D? In this case, it's moving horizontally, but there is friction. So in this portion, the gravitational potential energy stays the same, but there is work done on the system by friction. And because the work done on the system by friction is always negative, the total energy of the system is going to decrease. And because the gravitational potential energy is staying the same, the only way the total energy can decrease is if the kinetic energy decreases. Okay, so if we now let's look at total energy as we go from point A to point B. Now we have to define our system here. So here I'm telling you that you should consider the block and Earth together as a system, which means that you can consider the potential energy due to gravity. So as the block moves from point A to point B, what happens to the total energy of the block Earth system? That total energy is constant from A to B. Right, so the potential energy is decreasing, the kinetic energy is increasing, but those balance out, and there's no external work on the system. How about from B to C? The total energy is constant here as well. Again, no external work on the system. Finally, from C to D. Okay, hopefully you got here that at this point there is external work on the system due to friction, and so the total energy of the system would decrease because the work done by friction is always negative.
Solitude in E minor. Yeah, E